Now we are going to another interesting result. That is, when A is in BLH and A is normal, if x1 and x2 are eigenvalues of A, so eigenvectors of A, if x1 and x2 are eigenvectors of A corresponding to the distinct eigenvalues k1 and k2, x1 and x2 are the eigenvectors of A corresponding to the distinct eigenvalues, then x1 and x2 are orthogonal. x1 and x2 are orthogonal. How to prove this x1 and x2 are orthogonal? In order to prove x1 and x2 are orthogonal, we have to show inner product x1 x2 equals 0. Inner product x1 x2 equals 0 means inner product xy equals 0 implies and is implied by x and y are orthogonal. Okay, that's the product. That's the property of inner product. So how to prove this one? So it is given x1 and x2 are the eigenvectors corresponding to the distinct eigenvalues k1 and k2. Let k1 and k2. Let k1 and k2 are the eigenvalues of A such that k1 differs from k2. They are distinct eigenvalues. x1 with an eigenvector corresponding to k1 means there exists some non-zero x1 for n such that Ax1 equals k1 x1. Why? Because x1 be the eigenvector corresponding to the eigenvalue k1. Similarly, x2 be the eigenvector corresponding to the eigenvalue k2 means there exists some non-zero x2 for an h with a Ax2 equals k2 x2. x2 be the eigenvector corresponding to this eigenvalue k2. Okay. But what is A? A is normal. So what is Ax2 equals k2 x2? So what about A bar x2? So A star x2. A star x2 equals Ax2 star. A star x2 equals k2 x2 star, that is k2 bar x2. Okay, right. Then consider k1 into inner product x1 x2. K1 inner product x1 x2. K1 inner product x1 x2 equals inner product k1 x1 x2 equals inner product x1 k1 bar x2. That equals inner product x1 k1 bar x2 equals inner product x1. What is k1 bar x2? It is inner product k1 x1 inner product k1 x1 x2, that equals inner product k1 x1. What is k1 x1? It is Ax1. So it is inner product Ax1 x2. Inner product Ax1 x2 is inner product x1 A star x2. Okay. But what is A star x2? That is k2 bar x2. Inner product x1 k2 bar x2 equals inner product k2 x1 x2. Inner product k1 x1 x2 is inner product k2 x1 x2. That is, this can be rewritten as k2 into inner product x1 x2. K1 inner product x1 x2 is same as k2 inner product x1 x2. This implies k1 minus k2 into inner product x1 x2 equals 0. But we know k1 and k2 differs. K1 strictly differs from k2. So this should implies inner product x1 x2 equals 0 because k1 differs from k2. Inner product x1 x2 equals 0 means this x1 and x2 are orthogonal. Okay. So for when x1 and x2 are the eigenvectors of A corresponding to the distinct eigenvalues, then this then as these eigenvectors are orthogonal. Enough. Okay. Now we are going to another result. That is, when A is in BLH and A is normal, then every spectral value of A is an eigenvalue of A. Every spectral value of A is an spectral value of A is an eigenvalue of A. That means if A star equals if A star equals A star A, that is if A is normal, then when K following sigma A implies K following sigma E of A. When K following sigma A implies K following sigma E of A when A is normal. How? So this can be proved by K following sigma A. When K following sigma A, then, but we know that what is sigma A? We proved this result. We have sigma A equals, in previous class we proved this result, sigma A equals sigma A of A union set of all K such that K bar following sigma E of A star. So this is a well-known result. That is, this result is already proved in previous class. That is sigma A equals sigma A of A union set of all K such that K bar following sigma E of S. So when K following sigma A means, this means either this K following sigma by according to this argument, K following sigma A of A, or this K bar following sigma E of S. Okay. Now consider this argument. K bar following, if K bar following sigma E of A star, K bar following sigma E of A star, that means K following sigma E of A. Why? Because we proved this result. That is, every eigenvalue of A is again an eigen. So if K is an eigenvalue of A, then K bar is an eigenvalue of A star. Okay, that result is proved. If K is an eigenvalue of A, then K is an eigenvalue of A star. So K bar following sigma E of A star means K following sigma E of A. So K following sigma E of A, but we know that the sigma E of A is always a part of sigma. Sigma E of A is a part of sigma A of A. Okay, so clearly K following sigma E of A, but sigma E of A is a part of sigma A of A, so this implies this K following sigma A of A. Agreed. So when K following sigma A, then K following sigma A of A, but sigma E of A is a part of sigma A of A, thus every spectral value of A is an eigenvalue of A itself. Okay, so this is the theorems. If A is in BLH, A is normal, then if K is in sigma E of A, then K bar following sigma E of A star. And if x1 and x2 are the eigenvectors of distinct eigenvalues, then they are orthogonal. These two results are very important. Agreed.